Good morning, students. Myself, Dr. Pooja Yadav, and we were studying communication paper for electronics BSc students, SEM 5. And in this paper, we have studied what is communication, what are the types of communication. Is it okay with you? We have all seen what are modulation techniques, and from the last lecture, we have started our topic as optical fibers. Okay, so in the last lecture I have given you introduction about what is a optical fiber and how it looks like. I have given you a very good example of fiber optic cables also. You can see those cables in a showpiece. So the picture which is seen here, this picture, these are the optical fiber cables. Okay, from these cables the light is transferred or the light is carried from one place to another place. Okay, this is a type of communication network in which the cable is used, which is made up of optical fibers. Okay, so in these optical fibers we have seen the block diagrams also, that how the transmitter looks like and how the receiver looks like. So you all will be familiar with all. And in today's lecture, what we are going to see is how the light actually travels in optical fibers and what are the principles behind the traveling of light inside a optical fiber. Okay, so the term which is very useful for the traveling of light and for to pass the light from one place to another or from one end to another in an optical fiber is numerical aperture. So we are going to see all these parameters in detail in today's class. So we'll just move to our presentation, and we'll have an introduction of what is fiber optics. We have already seen what are fiber optics, but before starting, this is our new class, so before starting with numerical aperture and all, we will just have a look at fiber optics. So whatever, as I have told you earlier also, and this is just a mean of carrying the signal. Okay, just we are just talking about the channel or the cable, that is fiber optics. But if we have the transmitter, if we have the receiver circuit, and if we have the fiber optic cables, then we have a setup of a communication network. Is it okay? Your transmitter, your receiver will be having a very design, or they will be of that type if you are using the cable as fiber optics. And fiber optics carries nothing but light rays. Your data which is to be transferred from one place to another, it is to be in the form of light. Okay, so obviously we'll have to modify our modulator and receiver, or our transmitter and receiver, according to the data which is to be transferred. Okay, so first of all, whatever message we have to be transmit from one place to another, we have to convert it into light signal. Okay, then only will be able to use fiber optic cables to transmit that data which is to be which is modulated in the form of light. Okay, so this is the technology of using fiber optic cables. These are the bundle of glass threads. These are very tiny cables, just have the diameter as your hair diameter is measured. So whatever you are having in this optical fiber or fiber optics is nothing but light signal. Okay, and they are transmitted, they are to be carried from transmitter end to the receiver end on the principle of light traveling from one point to another. So we'll first of all we will say which bandwidth it covers in our electromagnetic spectrum. We have already seen electromagnetic spectrum when we have started our communication paper. So we have seen which bands are to be carried by amplitude modulation, frequency modulation. So here also we'll see once again what is the range of light in our electromagnetic spectrum. So can you see this spectrum? We are talking about this band. This is visible range. After IR and before UV you have this visible range, and our fiber optic cable, it works for the wavelength starting from 10 raised to power minus 5 to 10 raised to power minus 6. Okay, these are the wavelengths which our fiber optic cables covers. Okay, so you can see fiber optic transmission wavelengths, it has wavelength in nanometers. Okay, it ranges from 850 to 1550. So this is our electromagnetic frequency spectrum, and this band has to be, this band which is we are talking about, the this band is used in fiber optic communication networks. Okay, so we'll see once again what is the bandwidth of light used here. So here you can see that there are three types of light rays which can be used in a fiber optic cable. It ranges from UV to infrared. Okay, this all is, these all three types of light, they can be transmitted or they covers the transmission wavelength of fiber optic cables. So from UV you have UVC, you have UVB, you have UVA, and then visible lights are there. Invisible also you have from violet to red, and then in infrared. Okay, this ranges after 700 nm, you will have your infrared. Okay, from 100 to 400 we are having ultraviolet. Okay, so these are the, this is the frequency spectrum which we can see in our daylight. Okay, from this band we'll have to select the wavelength which attenuates less, and then on that wavelength we will transmit our data, or on that wavelength we are going to work on. Okay, so the first band on which we can work on a fiber optic cable is ultraviolet. It is beyond violet, invisible to human eye, and it causes sunburns. Okay, so UV, you all know that there are some disadvantages of ultraviolet light. Okay, so we'll not prefer ultraviolet lights for to carry our signal in within a fiber optic cable. Okay, then there is the next band which is the visible band, the light wavelength which the human eye will respond. That means that we can see these light rays which starts from violet to red, and the wavelength is starting from 400 to 700. And the last thing is infrared band. So here also we are having some harmful disadvantages of infrared also. So basically we'll prefer a band which starts at the very end of UV and it ranges till infrared. So we'll cover mostly the visible light in this spectrum when we are using a fiber optic cable. So what is ultraviolet? Band of light wavelength that are too short to be seen by human eye. We cannot see a ultraviolet light. Okay, we all know that if we are going outside in we are having exposure to ultraviolet and you will have sunburns. Okay, sunburns, and it is also not good for your skin. You will have skin tanning. Girls are so conscious about this. So this UV is what we are having some of the disadvantages, and it cannot be seen by our human eye. Okay, then what is next? Next is visible. It is the band of light which a human eye can respond, or we can see this type of light. So here The third band is the infrared band of light, wavelength that are too long to be seen, or we can see from here that we can see only the visible spectrum, the lights which are in the range of 400 to 700 nm. That band is only visible to our eyes. We cannot see ultraviolet, we cannot see infrared. Okay, so what is the band we are going to use in our fiber optic cable is mostly the visible light band. Okay, then which frequency we are going to work on fiber optic cables? There are some bands allotted for to be used in a fiber optics. So we have defined those band as, the bands name are O band, E band, S band. Here they are called as original, extended. Then we have the wavelength range also. It ranges from 1200 to 1360 nm. These are the wavelengths allotted to these bands. Okay, then there is E band, this is called as extended. There is S band, which is shorter wavelengths. Then there is C band, this is a conventional, or it is also called as erbium window. Okay, then there is L band, this is long wavelengths. And then we have U band, that is nothing but ultra long wavelengths. Okay, so these are some of the wavelengths allotted to the spectrum which we are going to use in our fiber optic communication. Then we'll go to the basics of propagation of light in a fiber optic cable. Okay, so we have seen the construction of transmitter receiver in the fiber optic communication in our last lecture only. In this lecture, we are basically going to study about how the light propagates in that short optical fiber, and what are the properties related to this transfer of light from one place to another in a fiber optic cable. Okay, so as you all know, there are some basics related to light rays, that light travels with the speed of light, and which is nothing but 3 into 10 raised to power 8 meter per second. So this is the speed of light. Thus the wavelength can be defined as lambda is equal to c by f. F is nothing but the frequency of light in hertz. Okay, and c is the speed of light. Then we can have the wavelength of light which is to be used. Okay, so what are the characteristic properties of light rays? There are some characteristic features of the lights which we have stated here, that light travels in straight line. You all know that light travels in a straight line. According to Planck's constant, we'll have E is equal to h into f, where h is the Planck's constant. This formula also you know, that the each quantum of a light contains energy proportional to the frequency of the light, and that is given by E is equal to, energy is equal to h into f, and where f is nothing but the frequency. Okay, and Planck's constant value you all know. So what are the other terms related to it? That is power, its wavelength, and in frequency in hertz. Okay, so whenever we are going to use any optical fiber cable or any network which is made up of fiber optics, so we have to consider all these parameters, okay, of light. Whatever light we are going to be transmitted from the optical cable, we'll have to first calculate all these parameters. We'll have to set first, we'll have to take copy pen, we'll have to do calculations, and then only we'll be able to design a particular network by using fiber optic cables. Okay, so these all terms are very important in a optical fiber communication. So light travels in vacuum or in air with the speed of light only, and it is 3 into 10 raised to power 8. Light travels in materials with slower speed than the speed of light. which is 3 into 10 raised to power 8. Like what we have seen, in air it travels with the speed of 3 into 10 raised to power 8, but if it travels through a material or any medium, it has speed lower than 3 into 10 raised to power 8 meter per second. What are the other properties of light? That it chargeless, does not interact with other light or can go through each other. So what is the advantage of this feature of light? That if you have a simple single optical cable, you can transmit 2 or 3 signals at a time, they will not interfere. Can be it is visible or is invisible. That if you are using UV band, so it will be invisible, and if you are using the visible light, that is in the range of 400 nm to 700 nm, you will be having the data which is visible to your eye. Then light can be refracted if it travels through two different media. Okay, refraction is the deflection of light. The path of light deflects or it refracts if it is transferred from one medium to another. Like if it is traveling from air to water, the light is getting refracted. Okay, a uh, visible light ray is reflected from a mirror or a highly polished plain metal surface, such as the reflecting surface of an aluminium foil. Okay, light can be polarized using polarization. Okay, you all know these are all the simple properties of light rays. What we are going to use in optical fiber is nothing but a light signal which is carrying our data or which is carrying our information. Okay, so all these property of light we are has to be, we will have to be calculate.
मैम
Refraction.
ऑडियो
Now what
क्लियर
is,
नहीं है।
hello, if you have
मैम
started
ऑडियो
please mute it on. Now what is
मैम
refraction? You know, we have given a definition of refraction in the last lecture also. So refraction occurs when the light travels from one medium to another, that is the light spreads out along its beam. Okay, and the index of refraction of the cladding is less than that of the core, causing the rays of light leaving the core to be refracted back into the core. In the last lecture, or in our previous class, I have told you that there are two different layers in a fiber optic. That first is the core and the second one is cladding. So what will we require is the light should not get out of the core, it should be traveling inside the core only. Okay, it should not go to cladding, it should remain in the core only, and it should travel or it should reflect back from the surface, and it should travel from one point to another. Okay, for that we'll have to select the refractive index properly of core and cladding. So this is how the lower refractive index region, light travels in a lower refractive index region, that it bends. This is the higher refractive index region, and this thing or this place is having a refractive index lower than this one. So the light is refracting, it is not traveling in the straight line, it is refracting in the medium. So this is the concept of refraction. We'll have to take a better look of light should not get refracted from the surfaces. That's why we'll have to take a much precaution over this property of light. Here once again there is the index of refraction, and the material which we are going to use, it should have a speed of light. That this is the definition of the index of refraction. It is known by you, or this is well defined by Snell's law of refraction. Okay, Snell's law tells us about how the refraction of the light should be there if we are using a material, if we are using two different materials. So what does the Snail's law say? When light travels from a material with one index of refraction to a material with a different index of refraction, the angle of incidence is related to the angle of refraction by this formula. This is n1 sine of theta 1 is equal to n2 sine of theta 2. This is what? This is the refractive index of material 1. This is the refractive index of material 2. This is the angle of refraction, and this is also the second angle which is related to the angle of refraction, and this is index of refraction. Once again, why we are stressing so much on refraction and its parameter is because what we need that our light rays, whatever we are entering from one point into our optical fiber cable, it should get total internal reflections only, it should not get refracted back. That's why we are taking much care of it, and we have some substances from where the index of refraction is also given. These are the constants of refraction we should use when we are using these materials. So we are just related to glasses, okay, because our fiber optic cable is made up of glass. So what is the index of refraction for glass? For that only we are much concerned. Now here I have given you the two examples of how the refraction look like. Here if you can see, this is the ray of light, this is entering from air to a material, so it is not being travel in straight line, it is getting refracted back. And here also when it is leaving from one material and entering into the other material, it is getting refracted back. Okay, so this is a very good example of refraction. You can see this type of examples in your day to day life also. And then we have a critical angle. This is also a very important parameter. The critical angle is measured from cylindrical axis of the core. The angle of incidence for which the angle of refraction will be 90 degrees. What is this? This is the critical angle for which the angle of refraction will be 90 degrees. This is called critical angle. Okay, so we'll have to measure what is critical angle whenever we are have incidence angle and we are entering the light or we are transmitting the light from the source into the cable. So this can be given as theta c. This is sine inverse of n2 by n1. This is how the critical angle is calculated, where n2 is the index of refraction for medium 1 and n1 is the index of refraction for medium 2. Okay, so here once again you can see from here that in fiber optic cable how the total internal reflection is there and how the refracted rays getting out of the core. That this is, these are the two layers of optical fiber. The internal layer is called as core and the outer layer is called as cladding. From here you can see at a particular angle or from this surface your rays of light, they are reflecting back into the core, and these the light rays which are entering at this incidence angle, they are refracting back. Okay, so what we will have, we should be considered or we are much concerned about these light rays which are traveling inside the cable because of total internal reflections. Okay, this is called as critical angle. The angle from where if you increase the incidence angle, it the light rays gets refracted back. Okay, so what we have, the incidence angle should be less than critical angle, then only the light rays will have total internal reflection. Is it clear to you? This is a very important point, and this is the basic of light rays to be traveled in an optical fiber. So these are some of the examples of critical angle. If the angle of incidence is less than critical angle, what will happen? This type of rays will get getting back to you. And this is how, if the angle of incidence is equal to the critical angle, this is where we will have the maximum refraction. And this is angle of incidence, this is greater than critical angle. So see, these are the two mediums, n1 and n2. So how the critical angle is changing, this is given over here, the three parameters of critical angle. Then once again we'll have reflection. Till now we have seen about refraction. Now we need reflect light to be reflected back into the core. So we'll see what is reflection. Is the change in the direction of a signal at an interface between two different medias when the light strikes or one material to the another material which is having different refractive index, then the light will be reflected back. This is called as reflection. The angle of incidence is equivalent to the angle of reflection. Okay, so this is how we have, if we are incidencing incident light rays, they should get back into the core, then only they will travel from one point to another. So what we will have inside the core, that is total internal reflection. Here in this picture, all the angles can be seen, that where is incidence angle, where this is the incident ray. Here the we'll have to take one normal, and from the normal till the incidence ray, the angle which is measured, it is called as angle of incidence. And after normal, if it is reflecting back, this is the surface of reflection. Okay, light is not refracting, it is reflecting. Okay, so from normal to the reflected ray, what we will take is called as the angle of reflection. Okay, so this angle of reflection is important for us. Then what is total internal reflections? How the light travels. Because of the total internal reflection, the light travels inside the fiber optic cable. So this is the picture. From this picture it will be very clear to you that how the light rays are entering inside the fiber cable and how they are traveling inside the fiber optic cable. This is light signal 1, and these are two different light signals from various angle of incidence. They are entering into the fiber. This is the core, not cladding. This is the core, and this is the outer diameter of a core. The one light ray is coming from this incidence angle, and they are reflecting back into the fiber optic cable. And the other light ray, this is incidencing at this angle, and they are also reflecting back, and they are traveling inside the fiber optic cable. And at the other point, the light rays will be cached, as you can see in this picture. Sorry, we'll go to next last slide only. So this is how the light travels in a optical fiber, and at the end or at the other end, you will see the light rays which is coming out of the fiber optic cables. Okay, so this is how the light travels in an optical fiber because of total internal reflection. Okay, so we'll have total internal reflection. Once again, from this picture it will be clear to you that what are the angles related to this. This is this is what we have: light rays at less than critical angle, it is absorbed in the jacket. we'll have three layers over here. We are having inside, that is called as core, then the second layer which is called as cladding, at the outer end we are having the jacket. Okay, so we should have the light rays, it should travel inside the core only. Okay, this is angle of incidence, this is the angle of reflection. Okay, from each point, when it strikes to the core, it gets reflected back inside the cable only, and then once again it will move to the core. So this is how we should have light propagation due to total internal reflection. So what is the core of or what is the concept of, or what is the basic of light traveling inside the fiber optic cable? It is nothing but total internal reflection. Okay, so this is a very good example, this is an animation also. Here what we are going to see is ki how the light propagates in a fiber optic cables in index profile. This is step index. Okay, we have seen step indexed and graded index optical fiber. So here you can see from the source, this is the transmitter end. From the source, the light rays, three types of lights, they are entering inside the fiber optic cable. This inside layer is called as core. The light rays are entering from three incidences, three angle of incidences. Okay, three directions you can say. First is which is traveling in straight line, so no need to worry about the light which is traveling in straight line. But if the angle of incidence is this one, you will have, there is total internal reflection. For the blue light and for the black colored light, this is not black colored, actually the wavelength will be different, but here it is shown by black color. So these two light rays, they are getting total internal reflections inside the fiber optic cable. Is it okay? Is it clear to you how the light propagates in an optical fiber? So here we'll come to numerical aperture. So what is numerical aperture? It is the measurement of the ability of an optical fiber to capture light. Okay, it describes the cone of light accepted into the fiber or exciting the fiber. Numerical aperture is the sign of the half acceptance angle. Acceptance angle means the angle from where the light can be entered into the fiber optic cable. So here numerical aperture is defined as sine of theta. This is an important picture. Sorry, we'll go to last slide. This is how the acceptance cone is to be shown. This is how we are having the acceptance cone. The light entering from this cone only will be traveled inside the core, or otherwise if we'll have the light rays which are not covered in this acceptance cone, they will get refracted from the core. Okay, so this is how we'll have numerical aperture and the angle of acceptance. Okay, so for this some conditions are there that how the numerical aperture should be minimized. So the light gathering ability of an optical fiber is determined by the square root of the difference of the squares of refractive indexes of core and cladding. So for whatever situations we'll have, whatever numerical aperture is there, what we will need, we'll have to select the refractive indices of core and cladding. They should match with each other so that the light should not get refracted back, or it should be there in the range of numerical aperture so that it should be traveled inside the fiber optic cable. So what is acceptance angle? The maximum angle within which the light will be accepted by an element such as a detector or a waveguide. Okay, so in the letter it is quantified as half the vertex angle of the cone. within which the optical power may be coupled into bound modes of a fiber, also called acceptance cone. Now one thing is also there, that if the light is traveling from one point to another, we'll have to couple that light, or we'll have to carry that light, and we'll have to give it to the detector element or to the waveguide which is carrying the light. So this is very important, that we should have acceptance angle or acceptance cone which is best suited for the detector or to the waveguide. This is how we can see here. This is the acceptance angle and this is the critical angle. Sorry, we'll have the, this is acceptance angle, means theta a, from normal to this and from normal to this limit. These 2 points or these two angle, they are very important. This is critical angle. Okay, this, from this the light is getting back or getting reflected in the core itself. This is the core and this is the cladding. It is having refractive indexes n1 and this is n2. Okay, so from this we have some related formula or some related terms which are important while calculating the terms. So this is index of refraction, Snell's law, critical angle, acceptance angle and numerical aperture. So these are all the formulas which is to be derived before having a communication network setup for fiber optic cables. We'll have to do all these derivations by selecting the proper refractive indices of core and cladding, and then we'll have to set up the communication network.